Hi everyone. So we are on day 24 of the challenge. Let's see what the problem is. So the problem for today is to build a conditional CGAN GAN model for generating specific images using the same fashion MNIST data. So we know what the data set looks like. We have already explored on day 22 and 23 this data set. So let's go and use the same context window. I'll say, hey, it is day 24 and here is the problem statement. So let's wait for the chat GPT to generate the response. Yep. Meanwhile, it is doing so. Let me go do what? Utilize the time and create file for today's problem. I'll say day 22.22.24.py. Add it to our Git repository. Mention what the problem is about. Problem is about building a conditional GAN model for generating the specific images. So it says, hey, a conditional GAN is a cool variant of the regular GAN, where you condition both the generator and the discriminator on some extra information like labels for the images. This means the generator is told which type of image it should create, and the discriminator is also known what type of images it expects to see. Let's dive into, so we are going to condition both the generator and discriminator in order to generate the images from the labels, like labels. So let's dive into this building the CGAN that generates specific categories from the fashion MNIST dataset. Uh, okay, so we'll have what all libraries will have to import. These all we have like already explored. This all we have already all of these we have already we know why we are using it. This also we know why we are doing it, and then we are going to build the generator, and then we are going to build the discriminator, and then we are going to build the conditional GAN. Uh, Conditional is to train the CGA, and we need to combine the generator and the discriminator while keeping the discriminator non-trainable we when training the full GAN. Okay, so we know why we do that. How are we combining it? I need to see that. So passing the 100 shapes, uh, and generate image from the generator, validate from the discriminator, and then define a model. Then we are going to train 1000 epochs, and then again the same loop that we had used yesterday. So let's do what? Can so what I'm asking ChatGPT to do what? Use too much yesterday's. Uh, I'm just asking which I see a lot of code from day 22, 23 problems. Can you tell which code is different here, uh, in short, so that I can just copy the previous code? Yes. Hmm. Okay, let's wait. Okay, it says a lot of information has been changed. We now take both noise and labels in the generator. We take both images and labels in the discriminator. We then concatenate and feed into the models. I'm saying the F fashion MNIST data set is too large. I can you suggest anything smaller data set that we can use today? If you remember, it took me like more than 2 hours to execute the train the model yesterday, and then even then were not able to generate the images properly. I don't want to get into the same problem again, so we can maybe use a different data set today. So it says we can use the MNIST dataset. If you remember, MNIST dataset has images categorized into 10 categories labeled from 0 to 9. Um, and yes, uh, I'll say give me the full code. So then we will build the generator, discriminator, and then build the discriminator model. Then we will add concatenate both the models to build CGAN, combine the models. This is what classification conditional thing we are doing. We are passing both noise and labels. Same with the images, and then correct. Let's what do what. Let's write the code without wasting the time. So I'll open it and start writing. Import TensorFlow as df, import numpy as npy, import matplot pyplot as plt, f from TensorFlow keras layers dense, import dense layer, flatten layer, reshape layer, leaky rectified linear unit, batch normalization, uh, convolutional 2D transpose, convolutional 2D input and concatenation, and then the models from TensorFlow.keras.models, import sequential and model, and then dataset from TensorFlow keras dataset. Here also, how many epochs are we running? We are running 1,000 epochs. It is the same thing. Don't you think so? So the problem is not with the epochs, but I guess the problem is with the. I'll what I'll do. I'll continue using the same fashion MNIST dataset as we have mentioned here in the original list, because everything is same. Everything is same. We are running 10,000 epochs. That is going to take the same amount of time. Why? Because even in the MNIST dataset, it has 60,000 images. So dataset import fashion MNIST, and then we are importing the Adam from TensorFlow keras optimizers, import Adam. Then we are doing what? Load and preprocess the data. And preprocess their data. This is X train, and then we want Y train. We want nothing and nothing, and then fashion MNIST load data. We already know how it looks like, so we are not going to look at it again. Now we are going to normalize the images to be in the range -1 to 1. We already know why we are doing that, so we'll do what? Let's copy paste the code from yesterday problem. Yes, we are doing this differently. We are encoding the y train to this digits. So let me see if they are like already, if they are already in the, you know what, if they are already in the digit form, numeric form, we do not have to convert into categories. So we do not have to use even a hot encoding. So I'm going to do what? Just the look at what is in there. Python run this day24. See, the data is already in the encoded version, so we do not have to. It is already in the numeric version, so we do not have to convert the categories into a numerical version. So now we are simply going to omit this step and build the generator. So I'll do what? Build the generator. So we'll do what? So the generator is conditioned on both the noise vector and the label, so it can learn to create a specific type of image. Okay, so let's code it up. Def build the generator. So I'll say let's get the noise input, and it is going to be an input type of shape of size shape 100. So it is going to be noise input uh, input type of layer with shape going to be 100. Then we'll have label. How many classes we have? We have 10 classes, no? So we'll say number of classes we have 10. We already know, so I'll just hard code it up. So then we are going to have label input, again input type shape here, number classes. Then we have concatenate noise and label. Concatenate noise and label. Concatenate. So model input is concatenate what? Noise input and label input. Now let's add the images, other layers. So let's first do what? Minimize the terminal and then add the images. So we are adding first image is going to be a dense image with what size? 7 into 7 to 256. We know that why it is, because we did something similar yesterday. It is going to be rectified linear union, and it is going to be model input. The class, the previous layer is going to be the input layer for this layer is going to be model input, and then we will reshape it back to 7 into 7 into 256. Hang on, yesterday also we got the error, so let's do that. And then this will be the input. Then we'll have the batch normalization of momentum 0.8, and this will have the input layer as X. Then we are going to unsample to 14 by 14. So we'll have unsample to 14 by 14. So we'll have X convolutional 2D transpose. We'll have 128 uh, neurons, kernel size 4, strides 2, and padding same. Kernel size 4, kernel size 4, strides 2, and padding same. And this will have input as X. The input layer is going to be X. Then we are going to have leaky rectified linear layer, and the alpha is going to be 0.2. This will have X as the input layer. And then we are going to have the batch normalization. Momentum is going to be 0.8. We know why we are doing that, because yesterday we did something similar. Now we are doing what we are doing, just copy it and do with 28 by 28. And if we do 28 28, and then it will become 64. So reducing the dimensions. And now final layer to create 28 by 28 image. Final layer to create 28 by 28 image output convolutional 2D, and it is going to be a convolution 2D layer. Kernel size is 7, and the activation filter is rectified linear unit, and the padding is same, and the input for this layer is going to be X. And then we will return the model as noise label as the one input, and the image output. The input is going to be noise label, and then image output. Correct? Perfect. Now let's build the generator, and then print the summary of the perfect. Done. Now we are doing what are we doing? The generator takes both the 100 dimensional vector and the uncoded input label. These are concatenated and fed into the model. Correct. Correct. They are concatenated and fed into the model. Correct. And used for sampling, which will generate high resolution images of 28 by 28 pixel from here. Now we are building the discriminator. This will also take labels as input along with the image to classify if the image is real. This will also take input a label as the input. This is the difference from yesterday. So let's do that. Build discriminator. So what are we going to do? Build discriminator. So we'll do what? Let me go image image input is going to be an input of dimension shape 28 by 28 and one, which is third channel, and one more channel for the grayscale images. And then the label input layer of shape number classes that we had in the generator also. So input number classes, not this. So let's do what? Process image. First we will process image. How are we going to process image? First we will flatten the images. Then we'll have 512 image neurons. and then the activation function is going to be leaky rectified linear unit. So first we will flatten the image. Flatten the image. Here it is going to be image input, and then we will have a dense layer of 5 and 2 neurons, and then we'll have a leaky rectified unit, linear unit, which will have alpha 0.2. We know what it means, why are we doing it. If you want to know, just watch the yesterday and day before that day 22's video. Now when we are done with it, now we are going to combine image and label. Combine image and label. So we are coming here. So first we are doing what? Label embedding. Label embedding, we are doing a dense layer of this size, and then this will have label as input. Then label embedding, then we will reshape it, and then we will combine it. We will combine the image, this image input, and the label embedding. Okay. So it is going to be label embedding. So dense layer of 28 size. The input for this going to be label input. Then we'll have label embedding, reshape it back to 28 1, and here the input is label embedding, and then we will combine both. Combine is going to be concatenate, not this this image input and label not label embedding. And now flatten combine input. We flatten the combine input. FALLATTEN. So what are we going to do? We will combine the input, then we will have 5 and 2 as the final layer. So the layer, and then we'll add the activation function. So we are going to have flatten it first. The input is going to be combined layer. Then we will add for the neuron 5 and 2 neurons, and then we add a leaky rectified linear unit layer with alpha 0.2 to the combined layer that we have created. Then we will have output layer, which will which will tell whether the image is a real image or a fake image. So that is why we have a sigmoid function. So output layer, so it will have validity dense layer with one neuron to tell whether it is an active false layer image or real image. Sigmoid, and the input is combined layer, and we will return the model same way as we have returned the image output, label input, image input, label input, and then the validity. Perfect. Now let's create the discriminator and build discriminator, and then compile the discriminator dot compile. Here we define the learning rate as 0.0002. If you remember, yesterday we were playing a lot with the improving the performance, so we adjusted the learning rate. So yes, that's what we are doing today also. Adam, the learning rate is going to be 0.0002. The loss is going to be a binary cross entropy, CROSS ENTROPY, CORS, and then we'll have matrix as what are we going to met? Wait, क्या? See, sorry, I have a cat. He's just being a little moody. Okay, so we'll have monitor the accuracy, and then let's just print the summary of discriminator. We are done with it. Now we'll do what? We'll build the conditional GAN. To train the conditional GAN, we need to combine the generator and discriminator. While keeping the discriminator non-trainable, yes, we did that, and we know why we did that, because we want to the generator to train and while to generate the images. So while we are training the conditional GAN, that is why turn off the trainable settings of the discriminator, and then we'll have input shape as 1,100 vectors and the number of classes. So noise input, label input, that we will pass to the generator to generate the images from the noise and label, and then we'll get the valid classify the generated images. We will pass it to the discriminator and the label input that we have created from the validity, and get the validity, and then we are going to combine both the models in noise input along with the noise input and label, and then we are going to compile. So build the GAN CGAN. I'll call it CGAN. So I'll put what? Discriminator dot trainable false, then noise, will say noise label to have an input layer of shape 100 vectors, then we have a label input, a noise input, label input. This we will have as input layer of shape and number classes. Then when we generate images from noise and label. So we'll do image generator, and then I'll pass this noise and label input, then classic generated image. So I'll call it as validity and pass it to discriminator. These images with label input, these images and label input, and below what? Define the combined model. Define the combined model. So it is called CGAN. Here we model, here we pass noise input and label input, and then we'll pass the validity, and then we are going to combine with the 0.002 atom learning rate, and then with the loss of calculated by the binary cost entropy. So CGN dot compile, here the optimizer is going to be atom with the learning rate of 0.0002, and the loss is binary cross entropy, and then we'll do what? Train the CGN. We're on the last step. Let's train the CGN. So what it is, it looks like what we did last time. So epox is going to, so I'll not go in detail because we already know what it is. 10,000 batch size, is going to be 32, and the save interval is going to be 1,000, And then we'll do what, label for real and fake data, and we will smoothen it. Yesterday we learned this technique to generate clear images from the to have more clear images generated from the generator. So will go and apply that today, that we had learned yesterday. Label for real and fake data. So we'll have real is going to be p dot ones batch size and one multiply by 0.9, and then fake is going, not fake np dot zeros batch size zeros. Of this batch size generate, okay, sorry, this correct. Then we'll do what, we'll go to each epoch, for epoch, in epochs, sorry, range in epochs. We'll do what, train the discriminator. So let me, yeah, what are we doing, we are generating the indexes. We did that yesterday also. We got the images for the real and the labels for the real images. We generated some random indexes. We got the from the training data we got the images and their labels. Then let's do what, generate. So indexes numpy dot rand int range is going to be 0 to 60,000, but I know it has 60,000, but let's not hard code it. Let's take it directly from the exchange dot shape uh, property, and of this size. So and then we'll have real images as xtrain with these indexes, and real images labels, so why train with these indexes. So we have got that. Now we are going to generate the noise. So noise numpy dot random dot normal 0 batch size, sorry, 1 0 to 1 range of size. The vector size is going to be batch size into 100 dimensions. And then the fake labels are going to be, this is something new that we did not do yesterday. So I'm going to ask, what is this line doing? Certainly. So let's, if we break it, the line of code is generating fake labels on training conditional GANs. Let's understand it piece by piece. So what this numpy.i is doing with number classes. This indicates that identity matrix, okay, of size numpy into numpy. Okay, this will create an identity matrix of this size. So in the number of classes equals to 10, then MNIST data set. This will create an, okay, so this will create an 10 by 10 matrix where each represents one hot and cold label. And this will generate a 10 by 10 matrix where each one line row will represent one hot and coded label. And then we have inside this a random dot choice, and what this is doing, it generates batch size random integer between 0 and number class -1, which is so it will generate 0 to 9 here of size this. So this will generate, for example, batch size 16, number class 10. This will generate output how many, 16 elements, 16 size vector, I mean 16 elements in one vector. and the range will be 0 to number n minus 1, which is 9. So this is it will generate. So the combination here, the combining both will be, uh, so number dot numpy dot I is being indexed by the random choice. For example, numpy dot random dot choice produces these, and we have, then the resulting fake labels will have one hot encoded for 3, this will be for 1, this is okay. Okay, so we are giving one hot encoded label for each fake image. Wow. Let's do that. Let's do that. Let's come back. Let's come back. So fake labels numpy.I. Here we pass what number classes. So this will generate our 10 by 10 matrix. And here if I pass numpy random dot choice, here we pass what generate from 0 to 9, uh, size of batch size, which is 32 elements. That's it. Now generate images. Generator dot predict. You will get noise, fake labels. Okay, so we pass the fake labels that we have generated, and then we also pass the noise that we have generated, and we are generating the images by using the generator. Then we calculate the loss. So this we did yesterday also. Loss, discriminator loss of real images, of identifying real images. We'll pass discriminator dot train on batch. What are we training on? Real images and real labels. Real images. So we have got the fake images, real images, real labels, and we'll pass real images. So the label is going to be real. Okay, then we calculate the discriminator loss of the fake images. So we'll discriminator dot train on batch. So we'll pass the generated images and the fake labels, and then we pass the fake original label, encoded labels, and then we do average it. We average it by what? uh, Multiplying it by 0.2, 0.5 multiplied by numpy add d loss real, d loss fake. That's it. Now we train the generator. Train the generator. We'll do what? We again generate the noise that we have generated like this. I'll just go and copy it, and then we'll do what? We'll do the same thing that we did it, but this time we are generating sampled images, and then we are doing what we did here for generator. We are doing generating the images from the CGAN model. So it is going to be generate, and we'll get the loss from the CGAN model. So we'll say CGAN dot predict, CGAN dot predict. So not predict, train on predict, train on batch. Here we need to pass what? Here we need to pass the noise that just we have created, noise and the sample labels, noise and the sample labels, and pass it as real images. That's it. Now we simply are going to display the images. Let's display the images. Display the images. How are we going to display? So we will display the images on 1000 epochs. So we will not generate for every epoch. We will generate only for the 1000 epochs. First we are going to print the what are we going to print? First we are going to print the epoch number, and then we will print the d-loss as d-loss, and the accuracy as as here accuracy is, oh, I guess that is done right. Accuracy as d loss 1 multiplied by 100, and then we'll have g loss percent, and we'll have g. Let's wrap it here like this, and then we'll have g loss as g loss. Simple, simple, right? Then we are going to have the generated images from the generator, not the generated images, generator predict on the noise that we have just created here and the sampled images. Then we'll have, then we are going to, if you remember, we normalize these images. Now we are just going to, I'll just copy it because we did it yesterday also, and then we just use the matplot library to plot the images in subplots of 2 by 2 size using the grayscale and show function. So that is it. Now we'll do what, we are going to run it. Python day 24, and we have an error here at line number here. It should work now fine. Let's run it, and we have error in line number 25. What do we have, what error do we have? Oh, so if we go to the line number 25, which is this, so noise input, label input, noise input, label input. So I'm getting this. So let's pass this to the chat GPT. What was the error? Oh, see, I guess I'm too much in. I'm really tired today, actually, but that should not be the excuse. So I ran 10 kilometers, then I went out with my parents to. I went out. My parents are here, so I wanted them to have a great weekend. So I went out. We explored Pune. We went to a lot of mandirs and temples and a palace also. So I walked like 30 kilometers. So yes, I'm extremely tired, but that should not be an excuse. But yeah, I still have an error at line number 116. Let's come to the line number 116. So this is how the line number 116 looks like. So if we go to the line number 116, let's go to the line number 116, which is the line number 116. Line number 116, line number 116. No, 2, 4, and this is the line number 116, which is what? 116 is when we are generating noise. Inside here, are we generating noise? My god. and here we have error. I guess this will be a problem here also. So let's fix that. Let's fix it and run one more time. And this is the error one. So let's this is how it is generating the real images and real labels. It will go real images with this we get from here, and real labels this we get here, and then we pass it to the real. Yeah, we are doing right. Let's go and understand what it is doing. Okay. Mm-hmm. Where are we using? So it says we can use something like this. It says to use this categorical thing here. So we need to add something like this. So there you are seeing indicates that the discriminator is receiving input that do not match the expected dimension for the certain line. Correct. Specifically, your discriminator is expecting input tensor with at least two dimensions, but it receives input that only have one dimensions. Uh, I'm just saying, can you give me full code, please? So I'm asking to give me the full code, please. Stop, stop. Can you give me full code, please? But on fashion NIST only. So yes, let's just copy and paste everything. Why? Because even if we'll be messing around with what and where it is making the problem, if I think we have not used the what 10H activation. Have we used the 10H activation for building? We have used activation called rectified linear unit earlier. Strange, but yeah, let's use it and see what it does today. Let's copy it, replace it here. Let's run it. If it fixes one hot encoding fixes the problem, then it's great. That's what we were missing. Yeah, so this is how the images are generated. I knew that this is how the images are going to be generated. So we might have to do the steps that we did yesterday, I guess. What we did is we generated the generator. We trained the generator twice on every epoch. Then we decreased the size of the batch, and eventually started having generating the uh, images a little clearly, and also started producing the loss for the discriminator and less more loss for discriminator and less loss for the CGAN. So yes, we know what it is doing, but what is the learning from this today is that we what we are doing is we are generating the images from the noise. It's also from for generator and the from the generator and the discriminator. So that's what we are doing today. Uh, yes, summary. If we go back to the summary, if we go back to the summary, if we go back to the summary. Let's go back to the summary. So the conditional GAN uses label information to generate specific categories of images. Yes, if you see from yesterday's and today's difference is that whenever we are generating images, we are passing the labels here. We are generating the labels and then we are passing the labels also. So today we are generating the images labeled with yeah, so with label information. So both generator and discriminator are conditioned on labels, allowing the model to learn together and classify specific type of fashion MNIST. We made use of transpose convolution layers in the generator to subscale the noise vectors and condition on a given level. So it is saying that we have used, if we see, see it is now generating the two, 2000th image is little better from the last image. And here if we go and see the output, here see the loss is getting better. It is increasing and it is decreasing, so this is better. We are applying the learnings that how to improve the GAN model that we did yesterday, we explored yesterday. I'm just curious to see where are we applying. See here, while unsampling, we are transpose using transpose layer. So yes, it was a great day. A little tired. I'm not in full energy. I guess the last 10 days of the challenge are not going that great as I had, as I anticipated. So yes, but tomorrow I'm looking forward to it. Tomorrow we'll be doing something different called cycle can for style transfer, which is, oh, tomorrow is going to be an interesting day. We will be doing a transformation. We will be transforming a horse to zebra conversion, and then horse to zebra, a smaller image set. So yes, tomorrow and day after that is going to be an interesting day. So yep, looking forward to it to build a transformation type model. And yep, thank you.